This video we're going to look at differential equations. A differential equation is just an equation which involves dy by dx and d2 or d2y by dx squared. We have seen differential equations before. Quite often we would have seen them where you started off with a gradient, the gradient function, and then you had to work back to get y, which was the equation of the curve. So it's something that we're not unfamiliar with, but what will be new to us is maybe the method we use in solving these equations. Okay, first example, we're going to do it the way we would have done it, first of all. So in the first one, it says solve dy by dx is equal to x squared. So the way we traditionally would have done a question like this, you would have just said your y is equal to, if I could get my pen working, you'd say your y is just going to be equal to the integral of x squared integrated with respect to x, which takes you to y is equal to x cubed over 3 plus c. And that is absolutely fine still for you to do that if you come across a question like this one. But just to show you a different method that we could use, apologies, just to show us a different method that we could use, we could have said, right, so I'm just going to write down dy by dx is equal to x squared, and what we're going to do is called separating the variables. Now I'm going to pretend as if this dy by dx is dividing. I know it's not dividing, but I'm going to cross multiply by it. So I'm going to have x squared dx. Now we know it's not dividing, so what we can do is just put an integration sign and then this makes this mathematically correct. So we go on from here, and what we have here, we're really integrating 1 by integrating it with respect to y. So if you integrate 1 with respect to y, what you get is just y. And on the right hand side, if you integrate x squared with respect to x, you get x cubed over 3 and plus c. Now I know in this example, definitely this is the easiest way to do it, but what we're going to be doing, separating the variables, is going to be the only way to do it. Okay, this what we have here with the c, this is called the general solution. If you were given a wee bit more information, and they have called it here a boundary condition, so for example, when x equals 1, y is equal to 0, then you could have worked out c as well. So without c, when you don't know what c is, so it's just written as the letter c, then it's called a general solution. But once c is evaluated, it is called a particular solution. So this is a general solution. If, for example, I work that thing out to be minus a third or whatever it happens to be, then that would be y is equal to x cubed over 3 minus a third would have been a particular solution. Okay, our second example, it says solve dy by dx is equal to y squared. Okay, so in this case, you've got your dy by dx is equal to y squared. Now, this would have been beyond us to use on the first method that I used in the first example there. Couldn't do it that way, so we have to separate the variables. Okay, so we're going to multiply across by the dx, so the dx is now going to go on the right-hand side, and this y squared is going to come across, and it's coming across this side, so really it's going to come across, and technically it's going to be dividing. So dividing by y squared is going to be the same as multiplying by 1 over y squared. So that's what you've got. And then put your integration sign around it, and that's it. So in general, folks, what you want to get is a function of y in front of a dy and a function of x in front of the dx. And this is a function of x because 1 can be a function of anything at all. Okay, let's just get this in index form before we do anything else. That's going to be the integral of y to the minus 2 dy is equal to the integral. I'm just going to write that 1 in to avoid any confusion, 1 dx. We'll sort out the right-hand side this time because it's easy. X plus c. When you integrate 1, you just get x, and then plus your constant of integration. When you sort out this side, when you integrate, you're just going to get y to the power of minus 1 divided by minus 1. So we'll go up here to finish this off. So that is left-hand side is the same as minus 1 over y, and the right-hand side is just x plus c. Notice I didn't put a constant of integration when I did this side. It's only necessary to put in one constant of integration because you'd bring both constants to one side and it would effectively become one constant of integration anyway. So just put it on one of the sides. Okay, so in general, if you have dy by dx is equal to a function of x times a function of y, then when you separate the variables, you're going to have the integral of the function of x times dx on the right-hand side, and 1 over the function of y times your dy, and that being integrated on the left-hand side. Okay, the next one, again, we're going to separate the variables. Remember what we've just said, we want the function of y to be on the left-hand side and the function of x to be on the right-hand side. So my function of y is going to be on the left-hand side, my function of x on the right-hand side. So if you've already got most of the x there, don't mess about with it, just leave it. So all I've done is I'm bringing this y across. So it's going to be your y comes across, it's multiplying at the minute, it's going to be dividing it when it gets to the other side, or the same as 1 over y. So you've really got 1 over y and the integral. So what you really have is ln of y is equal to, and this bit here, if you remember, we're in the form here, sorry, I'll just write that down, that's in the form of the integral of f dash of x over f of x, and when you integrate that, what you're going to get is ln of modulus strictly of f of x plus your c. So the right-hand side is just going to become, if we differentiate this bottom line, I should have got 2x, so this thing is half as big as it should be. So what I really get is going to be a half ln of x squared plus 1, and then plus c. Notice I've ignored the modulus, and then I've ignored the modulus because plus 1 is always positive, and x squared is always positive as well, so that's as good as I need to go. Okay, just on this one, we're going to continue, and we're going to change our c, just to show you a wee trick that we can do to make it look a wee bit prettier, basically, this question. So we're just going to say, I'm going to say, let c equal ln a. Now, people always ask, why can we do this? Why are we allowed to just change it? C is just a constant, so it's just a number which we haven't worked out just yet. And ln A is exactly the same. That's just going to be a constant that we haven't worked out. So we're just changing it, and you'll see why in a wee minute. So we're just going to rewrite this whole thing. We've got ln y, and all I'm going to do, I'm going to bring that half up, and it's going to become the power. So it's x squared plus 1 to the power of a half, and then plus ln A. So I've used my third rule of logs to do this, to bring this half up. Then I'm going to use my first rule of logs to combine this as one thing. So I'm going to be left with ln of y is equal to ln, and I'll put the a first, a upon x squared plus 1, and that's the power of a half. Now that looks a lot better. So you've got ln of something is equal to ln of something else. So it's a wee bit like indices. If you had 2x plus 5 is equal to x to the power of, 2x plus 5 is equal to 2 to the power of 10. 2 to the power of x plus 5 is equal to 2 to the power of 10. Therefore, you would know that x plus 5 is equal to 10. So it's exactly the same idea here. I have ln of something is equal to ln of something else, so I can just get rid of the ln's and say y is equal to a upon x squared plus 1, and that is the power of a half. Or you may not like that power of half, you could write a upon the square root of x squared plus 1. And that's it. Okay. Okay, example 4 here. Again, we want to separate our variables. We want to get a function of y on the left-hand side and our function of x on the right-hand side. So you multiply across by your function of y this time. This is actually going to looks like it's going to be a very nice one. And then the integral of x plus 1. So if we just go ahead and integrate this, you're going to get y squared over 2 is equal to x squared over 2 plus x plus your constant of integration. Now what you could do here is multiply through by 2. So everything gets multiplied by 2, so you'll have y squared equals x squared plus 2x plus, and a lot of people would write that as 2c. Remember, we haven't actually assigned a value for c yet, so we can just keep it as c and just know that this c is 2 times bigger, but you'd work your c out once you knew a bit more information, such as x equals 0, y is equal to 10, or whatever it happens to be. Okay, example 5 requires a wee bit more thought at the start. Remember our general idea. we wanted to have a start with this position dy by dx is equal to f of x upon g of y. So that's our starting point that we want to try and get to, and we're quite a bit off that starting point at the moment. So we're going to change this and bring the right x minus 1 squared times your dy by dx is equal to, and that's going to be minus 2, and I'm going to write that as y to the power of a half. So I've just brought that across to that side. Next thing I'm going to do is I'm going to bring my x term across. So that's going to be, if I bring it across, it's going to be x minus 1 to the power of minus 2. So we're now in this form over here. You've got an f of x and a g of x on the right hand side, and then I would start from here and try and work things out. So if I bring this y term across, I'm actually going to just bring the y to, okay, I'm actually just going to bring the y to the power of a half across. So it comes across, it'll now become, playing up. It will become y to the minus 1/2 times your dy by dx is equal to minus 2 times x minus 1 to the power of minus 2. And then we'll separate the variables. So the integral of y to the minus 1/2 integrated with respect to y is equal to the integral of minus 2 x to the minus 1 to minus 2, and that is times dx. Okay, to integrate this, we're going to raise the power by 1 and differentiate to see what we get. So I'm just going to try this at the side. So I'm going to differentiate x minus 1 to the power of minus 1 to see what I get. So if I do that, differentiate with respect to the power of x minus 1 to the power of minus 2. So I forgot to multiply by my power. So multiply your power and reduce by 1, and then times 1 inside. So that's not quite what I want. So therefore, if I differentiate 2 times x minus 1 to minus 1, I would get what I wanted. I would have got the minus 2 times x minus 1 to the power of minus 2. So that means if I differentiate this thing, I get minus 2 x to the minus 1 all to minus 2. That means if I integrate this, I will get 2 upon x minus 1 to the power of minus 1. So the right-hand side I've done, first of all, it is just going to be 2 times x minus 1 to the power of minus 1 plus your constant of integration. Left-hand side is a wee bit easier. Raise the power by 1, you'll go up to y to the power of a half, and dividing by a half is the same as multiplying by 2. Okay? What we have then, you can get rid of I'll just write that as root y, and I'll write it as 2 times root y, and then 2 over x minus 1, and plus your constant of integration, and just say you could write that as root of y is equal to 1 over x minus 1, and then plus your constant of integration as well. Okay, same idea in this example. I'm going to speed through this one a bit. You're probably getting a bit fed up with these examples. So this one, we have got, I'll bring the y's across first of all. You're going to have 1 over y plus 1 dy is equal to 3x squared dx. And then we're just separating the variables. The left-hand side, that's just going to be ln of modulus of y plus 1. Right-hand side is going to be x cubed plus c. Okay, it says this question giving y in terms, find a general solution giving y in terms of x. So really this is a wee bit of rearranging and changing the subject of the formula sort of work here. So first thing, you're going to have your y plus 1 is equal to, the inverse of ln is e, so e to the power of x cubed plus c. Now it's a very important wee example here to show us another wee trick here. So at this stage, we're going to say let e to the power of c is equal to a. So the right-hand side of this, we could really write this using your laws of indices. That's e to the power of x cubed times e to the power of c. So that's really 1 plus y is equal to a, because you said a is equal to e to the power of c. So we did this one of the previous examples. E to the power of c is just a constant. So a is also a nicer, prettier looking constant, basically. So you've got y plus 1 is equal to a times e to the power of x cubed. And then it says, giving y in terms of x, your last line, therefore y is equal to a e to the power of x cubed, then minus 1. And that's it. Okay, slightly different example, this one. This is one of the ones where it's actually a particular solution. So we're going to, at the end of this, we're going to have to work out your constants. So we'll see how we get on here. First thing, we're just going to start separating the variables. We're going to have our y squared times our dy is equal to sine squared x times your dx. And it's the integral of both of those things. Okay, we'll do the left-hand side. It's easy. It's going to be y cubed over 3, and the left-hand, or sorry, that was the left-hand side. The right-hand side is going to take us a wee bit more work to do. So integrating sine squared, have a look back a few videos ago on integrating powers of harder trig, I think it was called, and we use our double angles to integrate these ones. So by the double angle formula, cos 2x is equal to 1 minus 2 sine squared x. So if you rearrange that, you're going to get your sine squared x is equal to 1 minus cos 2x all divided by 2. So that means the integral on the right-hand side, I'm going to take the half outside, make it a wee bit easier, and that's 1 minus cos of 2x all integrated with respect to x. And everything here we can now integrate. Okay, that's to get rid of this half here. What I could do is just bring that, multiply across by that 2, bring it up here. So I'm just going to say that's 2y cubed all over 3 is equal to, and then I'll just get cracking integrating this. So integrate 1, you get x. Integrate your minus cos 2x, you're going to get minus a half sine 2x plus your constant of integration, c. Okay, it's probably as good a time as any to put your values in. So it says in the question, when y is equal to 1, x is equal to 0. So we might as well just put those in and see what we get. So the left-hand side is going to be 2/3. The right-hand side is going to be x is equal to 0, and sine of 0 is just going to be 0. So you've just got 0 minus 0 plus c. So you find your c is equal to 2/3. So run it a wee bit of space here, and we'll just say that means 2y cubed all over 3 is equal to x minus a half sine 2x, and then plus your 2/3. Now again, what you could do here is times through by 3 just to make it a wee bit easier. So you have 2y cubed is equal to 3x minus 3 over 2 sine 2x plus 2. And I'm just thinking it probably would be better to multiply 3 by 6 to get rid of that 2 as well, but it doesn't really matter. Okay, to finish this off, we've got really what's more like an exam question here. So again, solve this thing, giving your solution in the form y is equal to a function of x. So you make y the subject, basically. Okay, I'm going to start by just rearranging the formula. And I'm going to say then that you've got 1 over 3y upon y plus 2. The integral of that, sorry, dy is equal to the integral of dx. Okay, that then is going to be equal to, we have to change this. This is going to be a fraction. We're going to have to do this using partial fractions. So we're going to have to fix this. So I'm going to come back to this, call this equation 1, and I will come back to it. So I'm going to investigate 1 over 3y upon y plus 2. Say it is identically equal to a over 3y plus b over y plus 2. Therefore, when you multiply across, you're going to get 1 is identically equal to a upon y plus 2 plus b upon 3y. Now solve this whatever way you want. The easiest way probably is to let y equal to 0. That means 1 is going to be equal to just 2a. So your a is equal to a half. And also let y equal to minus 2, which means 1 is equal to minus 6b. So your b is equal to minus 1/6. So you've got your a and you've got your b. We can then go on and rewrite your equation 1. So just about left that on there. I'll get my equation 1. So equation 1 then becomes the integral of, it's going to be a half times, what was my a? Sorry, my a was a half. Yep, a half over 3y is going to be 1 over 6y. And then minus 1 over, and if you multiply in by that 6, you're going to get 6y plus 12. Probably the nicest way of doing it. On the right hand side of that is it was integrating x with respect, integrating 1 with respect to x, so it's just going to be x plus c. So that's what my equation 1 becomes. Okay, we can go on and integrate both of these things. Differentiate this bottom line. You should have got 6. So that isn't a 6 there. It should have been. So it's going to be 1/6 times ln of 6y. Likewise, differentiate this bottom line. You should have got a 6. We didn't. So it's 1/6 of ln of 6y plus 12. Let's put that in a bracket. And then is equal to x plus c. So what we can do then from here, first thing I would do is get rid of those 6's. So I'm just going to say, I'm going to just multiply across both sides. We're going to have ln of 6y minus ln of 6y plus 12 is equal to 6x plus, it really should be 6c, but remember we're just calling it c. And then on our left-hand side, we want to write this as just one ln function. So we're going to have ln of, and it's going to be 6y over 6y plus 12 is equal to 6x plus c. Okay, we should have enough room to finish this off here, hopefully. To do this then, first thing we want to do then is just tidy up the left-hand side. That's going to be ln of y over y plus 2. So just divided through 6 top and bottom, and then it's equal to 6x plus c. We want to make y the subject, so you've got y over your y plus 2 is equal to e to the power of 6x plus c. Now that, remember, is the same. Let your e to the power of c equal a. So really you've got y over y plus 2 is equal to a times e to the 6x. Look up one of the previous examples to see exactly how I've done that. Example 6, I think it was. And then go from here. We're still trying to get the y on its own. Haven't quite got there. I'm going to multiply across by my y plus 2. So it needs to be in a bracket. Without a bracket, it is incorrect. And then just multiply out and see where we go from here. So if you multiply out, you're going to have y times a e to the 6x plus 2a times e to the 6x. Now we're trying to get y on its own, so bring all the y's to one side. You'll have y minus y times e to the 6ax is equal to 2a e to the 6a. And then factorize to try and isolate the y's. So y comes out, leaving you 1 minus a e to the 6x is equal to 2a e to the 6x. And then your last line, and this is as good as we can go, that all divided, nice horizontal line, 1 minus a e to the 6x. That is as good as you can go, folks, because they don't give you any other conditions. They don't tell you when y equals 1, x equals 10, or anything like that. So unfortunately, we have to have an a in our answer, and that's it. Okay, that's a fairly hard example. Work through that one a couple of times just to make sure you know what's going on. And remember this wee bit up here, refer back to example 6 to see how I got from this line to this line. Okay, questions we can do. Differential equations exercise 1, and a list of questions there. 1, A, C, E, G, and I. So there's lots of ones that I've skipped out there if you want to do extras. And then 2, just A, C, and E. 3 to 11. And there's also the further practice differential equation sheet if you need any more help.